Okay, so in the first video, or the first part of the problem that we are going to discuss today, we have solved for certain variables, and so we are going to very quickly go over what we did in the first part of this problem after we talk about the system setup, and then we will take up a few more questions on this system. So this system consists of a cylindrical shell, as you can see, and there is a bar that goes through the midpoint of the shell along the axis of the shell. At a point B, the bar turns, or rather bends, and then at the end of the bar there is a disc. The disc is of radius capital R, and the bend of the bar is at an angle beta. Now the radius of the disc, the length of the part that is bent, and the angle beta is such that the outermost point of the disc, which is designated by the letter C, is in contact with the inner surface of the cylinder, and as the vertical part of the bar turns, the point C, which is in contact, rolls without slipping on the inner surface of the cylinder. So there is a rolling constraint at this point C. So what is given to us is this length L, this angle beta, this radius R, and it is also given that the vertical part of the rod turns with a constant angular velocity of capital omega as shown in the figure. So with this as the given conditions, in the previous video on this problem, we solved for two things, and that is the angular velocity of the disk, so the net angular velocity of the disk, and the angular acceleration of the disk. And in order to do so, what we did is that we used the XYZ, the rotating XYZ reference frame that has been specified in the problem. This XYZ reference frame is such that Z is along the bent part of the rod, and the XYZ is fixed to the bent part of the rod. It is not fixed to the disc. Okay, so basically you can imagine that the small x and small z, it forms a vertical plane at all times, and that vertical plane of course contains the inertial z-axis, which is the vertical direction, and then y is therefore always going to be horizontal, and it's going to be perpendicular to this vertical plane. And I'm talking about the small y-axis, so keep in mind that here we have a small xyz. So this is the small x, this is the small z, and then you can imagine that y is going to be such that you form a right-handed coordinate system. So with this rotating coordinate system, we solved for the angular velocity of the disk, and then we differentiated it to find the angular acceleration of the disk. In finding the angular velocity of the disk, we basically treated the disk as one rigid body, and C and A is the center of the disk and C is the point of contact, were treated as part of the same rigid body. And if we do that, then the relation between the velocities of C and A are given by this equation. Because C and A are part of the same rigid body, are being considered as part of the same rigid body, for this problem we don't need to add the rotating, or rather the relative velocity in the rotating frame. So with that we will move to the next part of the problem, and the next part of the problem is to find the actually let me keep this figure in front of us, at least as we start solving or posing the problem. So the next part of the problem is to determine the acceleration of the point C. So this is important, this is interesting, because we can see that the point C is denoting the instantaneous point of contact. Although this instantaneous point of contact by itself does not have any velocity, but it can have an acceleration, and it does have an acceleration, as we'll see. So our quest is to find this acceleration. So the way we will approach this is we will treat C and A to be part of the same rigid body. Effectively, which is true, C and A are indeed part of the same rigid body. However, there is a certain nuance. You can consider C and A to be part of the same rigid body and use that idea that they are part of the same rigid body to formulate the relative velocities, or you can artificially say that I'm not going to consider C and A as part of the same rigid body. I'm going to consider C to be a point that is translating and rotating with respect to A, and you can solve the problem that way also. So we'll look into that aspect as well. But first, let us start by treating C and A to be part of the same rigid body, and essentially what we are doing is essentially define our rotating frame of reference to be the rotating disk. So this is very important. Whenever we are solving problems on rotating frames, rigid bodies that are involved with both rotation and translation, we have to keep in mind, and we have to distinguish between two things. One is the rotating frame of reference, another is the triad. Okay, the rotating frame of reference is kind of a reference frame that we keep in mind when we are solving problems, and it is using that reference frame that we formulate how objects are moving with respect to each other. In particular, we formulate how, based on that rotating frame, we are going to formulate the angular velocity of the frame, we are going to formulate the relative velocity vectors, and so on and so forth. On the other hand, we need to contrast that with the triad. The triad should not necessarily be mixed with the rotating frame. They don't have to be the same. The triad is basically just a XYZ coordinate frame that is being used to denote all the vectors. So it's actually, the triad is probably a bit more secondary, but it's very important to formulate in the sense that if you don't have the triad, you don't have the ijk vectors, so you cannot express the vectors. But the reference frame is more fundamental in the sense that the reference frame basically is a frame where you need to put your thinking or do your thinking with respect to that reference frame to determine what is the angular velocity of that reference frame, angular acceleration of that reference frame, what are the relative vectors, and so on and so forth. So we need to distinguish between these two. So here we are saying, when we say that we are going to treat C and A to be part of the same rigid body, we are essentially saying that our reference frame is fixed to the rotating disk. Okay, so with this then we have the acceleration of the point C, which is what we are looking for is equal to the acceleration of point A plus alpha of the disk cross rho c with respect to A plus omega of the disk cross omega d cross rho c with respect to A. So keep in mind that because we are considering our reference frame to be fixed to the disk, we don't have to add the two more terms, the Coriolis term and the angular acceleration in the rotating frame term. So of the 5-term acceleration expression, it reduces to 3 because our reference frame is fixed to the disk. Okay. Now omega d and alpha d were all obtained in the previous part of the problem, and so we can just plug them in. Okay, so we need to plug them in, but I realize that in the previous video we set up the calculation of alpha d, but we did not quite complete the calculation of alpha d. So we are going to first do the alpha d calculation. Alpha d is essentially omega d dot, and if you go over the video, which is the part 1 of this problem, you will see that towards the end of the video is where we had formulated it. First of all, we had omega d was formulated, was determined. It was capital omega sine beta times L by R K plus I. So this was our omega d. This is the, by omega d what I mean is the net angular velocity of the disk, and it is being expressed using the ijk coordinate frame, which is more clearly given over here. You see the ijk coordinate frame is a rotating frame. The frame is not fixed to the disk. I shouldn't say it's a frame, it's more precisely a triad. The ijk triad that is being used is a triad that is not fixed to the disk, but rather fixed to the hub, or fixed to the bent part of the rod, okay, which forms the axis of the disk. So z is along that bent part, x is such that xz always forms a vertical plane consisting of the inertial z-axis, and y is mutually perpendicular to the two. Now when we find the angular acceleration of the disk, we need to take this derivative, and so this is our omega d. So the derivative is going to be capital omega sine beta times L over R K dot plus I dot. Now keep in mind that capital omega, beta, L and R, these are constant, and so we don't need to take the derivative. However, K and I are rotating, and so we need to take the derivatives of the two. So the question that we now need to ask is, what is the angular velocity of this triad, of this small xyz triad? So by definition, the xyz triad is simply rotating with an angular velocity of capital omega. It does not have the spinning angular velocity of the disk, because it is not fixed to the disk. It is only fixed to this rod which forms the axis of the disk. So therefore k dot is equal to omega xyz, which is the angular velocity of the rotating small xyz triad cross k, and this omega xyz is nothing but capital Omega sine beta in the negative z direction k plus capital Omega, well, let me see, this should be cosine, so let me just rewrite it. Sorry, this is, let me write it over here itself. Negative capital Omega cosine beta k plus capital Omega sine beta I, and this would be cross product with k. So we have the following: k cross k is 0, so I cross k is minus j, so we will have negative omega sine beta j. So that's our expression for k dot. Similarly, I dot is omega xyz, and note that this omega is different from the angular velocity of the disk. This cross I is what we need to do, which is going to be this same expression cross I. Well, I cross I is 0 and k cross I is j, so we will have negative omega cosine beta j. And so we can plug this in here, and what we will get is that the angular acceleration of the disk is given by minus omega squared sine beta times L over R sine beta j plus cosine beta j. So both in the j directions, so we can actually simplify this and say that it is negative omega squared L over R sine squared beta plus sine beta cosine beta j. And let me just demarcate this part. Okay, so now we have the angular acceleration as well of the disk. So now we can go on to the implementation of this equation, which will give us the acceleration of the point C. So I'm going to move this page up, and whenever needed I'll bring up the picture, but in the interest of getting some space I'm presently moving that picture out of the view. Now let us consider the acceleration of the point A. So to discuss the acceleration of the point A, let us go back to our picture. Alright, so note that the point A, which is over here, so I am referring to this schematic here, which is same as this schematic, just written or drawn a little bit more clearly with bigger letters. So note that the point A is essentially just going around a circle at a constant speed. Okay, and that speed is given by the angular velocity omega times this distance, and this distance is capital L, because capital L is the length of the bent part of the rod. So capital L sine beta. Capital L sine beta is this distance from the point A to the vertical axis. So capital L sine beta times omega is the angular velocity, and it's it's the linear velocity of the point A, and it is going in a circle with a constant velocity. So its acceleration is just a centripetal acceleration directed towards this axis, okay, in the horizontal direction. So essentially the acceleration of the point A is towards, in the horizontal direction towards this axis, and it is omega squared L. So let me just make some space here so that we can write. So it is omega squared L sine beta. Now we need to resolve it along this x, this z and y. Now it is going to be directed in this direction, which means that if I take the cosine, it is going to be directed along the x but with the negative x direction, so negative cosine beta I, and it is going to be sine beta in that direction, so negative sine beta k. Again, note that the I, j, k that I am using are referring to the triads, not my rotating reference frame. Okay, and my triad is the small xyz represented by the unit vectors I, j, k, and the small xyz are fixed to the bent part of the bar, which is of length L. It is not fixed to the disk. Okay, so that's good. So referring back to this equation, we have the acceleration A, we have alpha d, we have omega d, and we have now rho c with respect to A is going to be very simple, because in our case we are considering if you consider this diagram, then C is going to be always at a distance of r, and it's going to be in the direction I. So essentially C with respect to A is Ri. Alright, so now it's just a matter of plugging in all the expressions, and in the interest of time I am going to skip the algebra here. Let me just check if my algebra was vector algebra was good. So I have substituted for okay, so I'll skip the algebra in the interest of time, but essentially if you go ahead and let's call this equation 1. So plugging in A sub A alpha d rho c with respect to A and omega d into 1, we obtain acceleration of c to be omega squared sine beta times cosine beta plus L over R sine beta times RK, sorry, RK, not RI, minus LI. Okay, so this is R in the K direction and minus L in the ith direction. So let me just write it a little bit clearer here. Acceleration of C is equal to omega squared sine beta times cosine beta plus L over R sine beta times RK minus Li. That's the acceleration of the point C. Okay. All right. So now what we'll do is we are going to consider some alternate methods of solving this problem. And this is important because unless we try out these problems or explore the solution of these problems by taking alternate approaches, the fundamentals of dynamics may not clearly crystallize, and that's why in that direction what we'll do is we will now do a sub problem of this, where we will say that I want to solve the angular velocity of the disk as we have done here. See, this was the first thing that we had solved. We set up the problem and we found the angular velocity of the disk. In fact, we found the spinning speed of the disk by setting the velocity of the point C to be equal to 0. Recollect that initially phi dot was not known to us, and you will find that in the first part of this video we had first solved for phi dot, and the question that we now ask is, how can that same phi dot be calculated if instead we considered the points A and C to be just 2 points. So let us say that our rotating reference frame, we are now referring to the rotating reference frame, not the triad. Let's say that our rotating reference frame does not consider, is not fixed to the disk, but rather it is fixed to the bent part of the rod. So it is fixed to BA. Okay, it is not fixed to the disk, it is fixed to BA. And so essentially our rotating frame of reference is now coincident with our XYZ rotating XYZ triad. So you can now see that the triad and the reference frame are two different things. When we solved this problem earlier, we considered the rotating reference frame to be fixed to the disk, okay, and the triad was not. Now we are saying that the rotating reference frame is not fixed to the disk, but rather it is same as the triad. Okay, so now if we take this then and find out phi dot, we should get the same value of phi dot because our triad remains the same. It is our reference frame that has only changed. So let us formulate the problem and find out the value of phi dot and prove that we get the same value of phi dot. Okay, So a couple of things first. So the next question that we ask is, find the spinning speed phi dot with rotating frame of reference fixed to AB, i.e. the bent part of the rod, and not fixed to the disc. Alright, so if we do this, then again, just for the sake of reference, I'm going to have this picture because it's going to be critical. Our rotating reference frame is now fixed to this bar AB. Okay, so in this rotating reference frame, C is not being considered, C and A, or C is not part of that same reference frame. Okay, so essentially, when we express the velocity of C with respect to A, we will have to introduce the relative velocity within the rotating frame, because our rotating frame now does not rotate with the disk, and because it does not rotate with the disk, there is a relative vector in the rotating frame of the point C with respect to A. Okay. So if we now express VC equals VA plus omega of the frame cross rho C with respect to A, now we need to have the third term in the velocity expression, which is the velocity of C with respect to A in the rotating frame. Okay, now if you consider the rotating frame, imagine that you are looking from B towards A. So this is A and you are looking from B towards A. Okay, you are looking down on the disk, and imagine that C is over here. Okay, because you are not rotating with the disk, with respect to AB, you will now perceive C to have a velocity because you are not fixed to the rigid body. Okay, you are observing the rigid body from above. Okay, and you are not moving with the rigid body, and the velocity with which C would be moving with respect to A is going to be due to the spinning speed, and it's going to be R phi dot. Furthermore, the angular velocity of the frame in this case is going to be the angular velocity of the XYZ triad, because you are indeed fixed to the bar AB, and the angular velocity of the triad is we just wrote it in the previous page. Let me just check. Negative omega cosine beta k, so it is negative. Okay, so omega frame for this frame is going to be negative omega cosine beta k plus omega sine beta I. So this is now going to get plugged in here, rho c with respect to a still remains the same. It is Ri because our coordinate triad has not changed. The velocity Va will also remain the same. If you check with the first part of this video, you will see that the velocity of A is minus L sine beta omega capital Omega J. So this remains the same as well. The only change now that we need to consider is this the velocity of c with respect to a in the rotating frame, which is r phi dot. And if we consider this this figure, then r phi dot is the velocity with respect to a by virtue of this rotation, which is pointing in this direction. R phi dot is going inwards, so basically rho c with respect to a dot in the rotating frame is negative r phi dot j. Okay, so if we now plug in these expressions here, we will have negative L sine beta capital Omega J. Now we need to do omega frame cross rho c with respect to a, so k cross I and I cross I. Well, I cross I is 0, so k cross I is j, so we will have negative omega cosine beta capital R j, and then the last term is negative r phi dot j. And if we combine these, we see that all of these components are in the j direction. So if we combine these, we have let's see, we will have negative L over R sine beta plus times omega, plus omega cosine beta plus phi dot capital R times j. And so in other words, phi dot is equal to, and this is equal to 0 because the point C has 0 velocity. It has a rolling constraint, rolling without slipping. So phi dot is negative omega times L over R sine beta plus cosine beta. Which is the same expression that we had in the first part of the problem. So this indeed shows that you can change your rotating reference frame, and when you change your rotating reference frame, you need to go back to your original 3-term velocity expression and evaluate to see which terms need to be there and which terms may drop out. In this case, our second choice of the rotating frame mandated that we include the rotating or the velocity, relative velocity between C and A in the rotating frame, and that was included. Our rotating triad remained the same, and so when we did the vector multiplications and additions, we did come up with the same expression for phi dot, which is the spinning speed. And so this again goes on to show that we can solve these dynamics problems using multiple methods, multiple approaches, and we can in each approach we can try out different types of rotating reference frames. We could also try out different triads potentially, which we did not do in this case, but you can, and then solve the problem and see if the answers are consistent with each other. And that's actually a pretty good way to learn dynamics and the techniques of dynamic analysis. So we'll stop here. Thank you.